Let's start. Okay, let's begin. So again, so far in this course, we basically started off with a single stage op amp. Then we saw that was not good for driving resistive load. So we put two stages. Then we saw it needs to be compensated to make sure stability. And then we saw that single-ended output had some issues. So we went for fully differential op amps. And we saw common mode feedback to stabilize the bias and common mode. And again, if things were all nice and good, there is no need to teach anything further, course ends there. But unfortunately for you guys, or fortunately for me, that is not the case. Because it turns out, in practice, there are a whole lot of things that work against you. As a designer, you have to take into account all of those non-idealities and then make sure your design works in presence of all. Right? And we'll look at few of them in the rest of the course and see how we can tackle. So, the first non-ideality that you should be aware of is there is nothing that is truly linear. Everything is non-linear. Right? Second, noise is everywhere, starting from electronics to classroom setup. Everywhere you have noise. And third is there are no two things that are exactly identical to each other. There will always be some kind of mismatch. Okay. So we'll start looking at each of them one by one, starting from mismatch, and then we'll go in this order. To appreciate mismatch, it is nice to understand how things are made on CMOS chip. That is how each component is basically made on a CMOS process, right? So we'll look at that first. We'll start with the MOSFET. MOSFET, this is our hero. I'm sure you guys know how a MOSFET is made. So you have a huge P substrate. For an NMOS, you have two heavily doped N plus regions like this. And then you have the polysilicon. On top of it, you have the metal layers. Right? And of course, to make contact with this, I mean, this is one of them is source, other is drain. To make contact with the source or drain, you again put metal contacts and then take out. Right? This is NMOS. I mean, I always say this looks like a cool robot like this. Right? Yeah. But anyways, so this is with NMOS. Similarly for PMOS, what do you do? How is PMOS made first? Yeah, but yeah, correct. You have to have a first deep N well, and then you put two P plus things and then do the same thing. Sorry. And in addition to this, to make connections, you have a whole lot of metal layers. You have, let us say, this is some bottommost metal. This is one more metal layer at the top. So we'll have a whole lot of metal layers, a number of metals available for making connections. That all depends on the particular process. Okay. And even the thickness you have for these metals, the spacing between the metals, and in general any spacing in this vertical dimension, they are not under your control. It is fixed by the fabrication process. So the only dimensions that you have control over are the other two sides. So this side and this side. And that's why typically, although this is strictly a 3D thing, we draw the top view of this guy looking from the top, because that gives you the two dimensions that are under your control. And if you draw it, it's your first year engineering drawing. If I draw the top view, I'll have for a MOSFET, this is the polysilicon, and then this is your source and drains. So this is the length of the MOSFET. This is the width. Right? Great. So next, in addition to MOSFETs, what other components do we need for making circuits? You need passives like resistors and capacitors. Let's look at resistor. So resistor, multiple ways it can be made. Let us say one way is to have a high resistivity material like a special polysilicon. You have something like this and then use it as a resistor. So if I mark the dimensions here as, let us say, length, this is W and this is T. what is the resistance of this piece of material? If I give you the dimensions, how will you find the resistance? The rho L by A. What is rho? What is the length? The cross sectional area is T times W. And as I mentioned before, this vertical dimensions is not under your control. It is fixed by the fabrication process. So I can take these two guys out. Right. So now this guy, the resistivity by the thickness you have has a special name that is called the sheet resistance. That simply says if you take a material which has the same length and width, what is the resistance of that portion? That's all. So basically, if you draw the 2D picture of this, you will have something like this. So let us say maybe L. So this is the length and width. So essentially, if you choose the length to be same as the width, the resistance of this piece is the sheet resistance. And what is the units of this? Yeah, I mean strictly speaking it is ohms, but typically we say it as ohms per square. To denote that, it is basically the sheet resistance. And the idea is, if you know the sheet resistance, you find how many squares are there within this. Sheet resistance times the number of squares you have is the total resistance. That's all. And again, if you want to know typical values, it can change, it can vary anywhere between 50 ohms to 100 ohms per square. It again depends on the particular process.
So that means that the width of each line should be the same.
Width of each line meaning?
Width
Oh sorry, yeah, this is width. This is width.
For all the lines that we conducting lines that we create, the width should be the same.
No, not necessarily. Why do you think that? Why did you say that?
Ohm per square.
Correct. So basically, see, okay, that's why let's take an example, right? So let's say you want to have, let's say your sheet resistance is say 100 ohms per square. Let us say you want to make a resistance of 1 kilo ohms. What it says is this ratio should be what? 10. That's all. So now again, you have infinite possibilities. You just have the ratio of this to be 10. You can choose length to be something and choose the width to be appropriate. So as of now, we don't know how exactly to choose length and width individually, because we just have one equation governing the two. Later we'll see what might be another criteria which you might use. But this is about resistor. Okay, it's quite simple. And the other passive we are interested in is capacitor. So how do you think we'll make capacitors? Yeah, I mean two metal, I mean whatever, metal insulated, metal kind of structure. So, but again, if you recollect, in your CMOS process, this is your P substrate. You will have a lot of metal lines. So let us say this is the two metal lines in the bottommost stuff. These are the two metal lines in the top two layers. We can essentially form a capacitor between the bottom two layers or the top two layers. Right? Both are equally fine. But you know that if you have a CMOS process like this, the P substrate, which is the common body terminal for the NMOS transistor, that is connected to ground, right? So now if this is connected to ground, whenever you have a metal line like this, that will have a parasitic capacitor from that metal to the substrate, right? So anytime you form a capacitor, you not only have this capacitance formed between the two metal lines, you will also have an extra parasitic capacitor, let us say, from each of the metal lines to the substrate, right? And of course the bottom plate will have the largest parasitic capacitor because it is closest to the P substrate. So if this is the case, which of these two do you think is better? Okay. Do you think forming the capacitance using the two bottom metals is better? Top one is better because the parasitic capacitance from this metal to the substrate is going to be very small. So typically that is why it's done in the top two metal layers. And in many processes, you will have two reserved metal layers in the top, metals just for making capacitors. Right?
Sir, so won't there be parasitic capacitance between two different metal layers?
That will also be there. Yes.
So how can we?
Yeah, that's why typically you have a separate two metal lines reserved on the topmost. This will not be used for routing. For example, the metal lines you will be allowed to use for routing could be limited to somewhere here, and these two might be reserved only for making capacitors. And this basically, if you actually see, right, the spacing will actually keep increasing as you go to higher metal layers. That is not under your control. Typically, you will find that the spacing, this distance from, let us say, the topmost metal layer to the layer below, that will be quite large, so that you don't have this parasitics so much. So yeah, so now the capacitance is straightforward. You just have two metal lines, metal plates. Let me take you to something. You have two metal plates like this. You put some dielectric between them and form the capacitance. And if the dimensions are length, width, and d, what is the capacitance of the structure? Yeah, let me just, epsilon times the area. What is the cross-sectional area of the plate? By the spacing d. Again, as I mentioned, this spacing, vertical spacing, is not under your control. So if I take all those things that are not under your control separately, we'll have something like this. And this is typically called the unit capacitance, which tells the capacitance per unit area of this particular structure. So, and again, this number can range anywhere from 1 femtofarad to 10 femtofarad per micrometer square. Right? Cool. So now you have now you know how things are made. So now let us say you take your circuit, you have MOSFETs, capacitor, resistors, you put everything, decide where each one is going to be there, make connections. Of course, you send it for fabrication. So we don't fabricate one chip or two chips at a time. As you know, you do a huge silicon wafer, and typically this can be having a diameter of about 300 mm. And on this wafer, finally you go and dice it like this. I'll just roughly show it. So each of these guys is your actual chip, right? So depending on the dimension of your each chip and this one, in one wafer you will get so many thousands and millions of parts, right? So let us say in this particular chip, let us say now I have a case wherein I have a particular resistor in that particular chip, and let us say it has a value of 1 kilo ohm. Similarly, let us also consider a MOSFET in that chip, and let's say it has a nominal threshold voltage of say 0.4 volts, and this mu n C ox W by L, let's call it as beta, the current factor. This is something, and let's also consider a capacitor. This is nominally, which is supposed to have a value of 100 femtofarad. Now in the same design, let us say I have an identical resistor placed close to this. What do you expect the value of this guy to be? You expect that it should be 1 kilo ohm, but as I mentioned in the beginning of the class, there are no two elements which are truly identical. There will be some kind of mismatch. So in practice, the value of this guy might not be the same as this value. It might vary slightly here and there. And the simple reason is because in each of the steps in the fabrication process, there will be something different happening for this guy and this guy, right? You can't guarantee that whatever happens in this location, exactly the same thing will happen here, right? Again, one simple way to understand this, see here I have drawn nice rectangles for the resistor, but in practice you can't etch out rectangles. You will have lot of rugged edges like this. So you'll have something similar happening here also, but you can't guarantee that what's happening for the top resistor will happen exactly for the bottom resistor. So you'll have variations in the resistor value. So now let us say I have 1000 such identical resistors in my design. If I find the value of all the resistors, they will be slightly different from each other, right? And if let us say plot the distribution of these resistance values, that is, in the x-axis I have the possible values of the resistors. Oops. Okay. Let me just close it. Yeah. So let us say in the x-axis I have all possible values for the resistors, and in the y-axis I plot the number of resistors having that particular value. How do you think this distribution will look like? Gaussian distribution, again central limit theorem. We have a lot of independent, identically distributed random things adding up. Here also same thing. You have a lot of multiple processes are resulting in this randomness. You'll find this. You'll have a Gaussian distribution like this. And what do you think the mean value of this guy will be? Yeah, it's expected that this to be 1 kilo ohm. Around this you'll have a spread, and this is typically called the random mismatch. Now on top of it, you will need to have, you will also have another kind of mismatch or another variation. So here, let us say now I considered the this chip, right? So here I found that the resistors have a mean value of 1 kilo ohms. Now let us say I took a chip from this corner. Here if I find the mean value of all the resistors there, you will find that need not be 1 kilo ohm, that could be say 1.2 kilo ohms. Similarly, if I take the chip from this corner, here it could be some 0.8 kilo ohms. Again, the reason is the same. In the fabrication process, whatever is happening, you can't expect that same things are happening in each of these locations. There will be something different happening for this guy, this guy, this guy, and so on. Because of this thing, you will have variations in this. Okay.
So you want 1 kilo ohm in all the chips?
Nominally, you would have designed it for 1 kilo ohm, but what you will find is that if I take the mean value of the resistors, that will be different in each of the chips.
In that chip also, that blue chip also, there you also designed for 1 kilo.
Yeah, basically, see, all of this will be the same design, right? In the wafer, you will have the same design put in all the chips. So I nominally you expect that each of this should have a mean value of 1 kilo ohms, but once again, due to the variations in the process, you will have difference in the mean value also. And this is typically called the process variation. So what this means is, say in the first chip, if I look at the mean value, distribution of the resistors, it will have a mean value of 1 kilo ohm. If I take, let us say, some other chip in the same wafer, the mean value could be 1.2 kilo ohms. For some other chip, it could be 0.8 kilo ohms. But the foundry will guarantee that in that wafer, if I take any chip, the mean value will be within a range. And let us say that range is 0.8 to 1.2 kilo ohms. That is something you know. What is the range this mean can take? That the foundry will give you data. So now if I take any random chip in the wafer, one can have a distribution like this, one can have something like this, and so on. The mean can be anywhere in this range, and this variation in this mean is referred to as the process variation. That is basically chip to chip variation.
So we can also say the same thing about the widths, the lengths of the
Yeah, same thing. We'll come to that. Now we are talking about resistor. Same thing will happen for each component. And on top of it, in a particular chip, around the mean value, you will have variation. That is what is referred to as the random mismatch. So this guy is basically intra chip or intra die variation. And not just that, right? Let us say here, if I take one wafer, let us say I took chip in this location. For this guy, I find that the mean value of the resistors is 1 kilo ohm. Let us say I process second wafer, same design. I took the exact, chip in the exact location in the second wafer. For that also, I can't guarantee that the mean value is 1 kilo ohm. It can be different. Right? It's like every time you cook something, can't expect that the taste will be identical, right? There will be some variations here and there. You will put salt like this, something. Right? Cool. Yeah, and like you pointed out, I told with only resistors, even for MOSFET, if you take, for a MOSFET, finally we have, let's say we're interested in the properties which are threshold voltage and the current factor. So again, it will have a Gaussian distribution like this. Within a chip, you will have variations, and from chip to chip, you will have process variation. Same for the capacitance also. Okay.
So plotting this distribution, what is the width and length of the resistance that we are using?
Let us say you take something. What I'm saying is you take some width and length that supposed to give a nominal value of 1 kilo ohm. I have 1000 identical copies of this, let us say. That will have a distribution like this.
So if we take a width and length such that it gives a resistance values of say 5 kilo ohms, then the distribution can be different.
It will be Gaussian. It will be Gaussian, but spread will be, they will come to that, yes. We'll see what will happen to the spread, yeah. But the idea is, it's kind of, again, loosely speaking, central limit theorem holds and everything will be Gaussian in practice. Right? Great. Cool. So now, let us say, what can we do? Yeah. I have let me just summarize it, right? So let us say now for a MOSFET I take, as we saw, oops, sorry. Yeah. The let us say you take the threshold voltage, current factors, etc. Nominally, you expect them to be at a typical value, and this is called the typical case, or T. So this threshold voltage and beta are of the nominal value you expect, and due to process variation, this value can be different. And let us say the threshold voltage and the current factors are in such a way that the current in the transistor is very small. If the current in the transistor is small, what can you say about the speed of the transistor? Slow. So that gives you to this extreme, wherein we call it to be at slow. Similarly, if the threshold voltage and the current factors, the mean value of them vary in such a way that the currents are faster, so we'll have a fast case. So that's what we call as F. So this basically is for an NMOS case. So similarly for a PMOS transistor, you will have same cases. So now you put combinations of this, you will have 5 cases, and that's what we call as process corners. So what we do is, let us say here I plot for NMOS, here I have for PMOS. You can have a case where both of them are slow. You can have a case where both of them are fast. You can have a case when one of them, NMOS is fast, PMOS is slow. Similarly, you can have a case where NMOS is slow, PMOS is fast, or both of them being at the typical. So these are called the process corners. Now, in addition to this variations in the process, you will also have variations in the supply voltage. You will also have temperature varying all over the place, the ambient temperature. So typically this is called as the PVT variations. So as a designer, your job is to make sure that your design is robust and works across all these PVT corners, right? You can't design something and say that it will work only in South Africa It should work both in, like Rajasthan, it should work in Kanpur, Kashmir, wherever all possible extremes of temperature, it should work. Okay. Cool. So, basically to summarize, if you have any component value you take, within a chip you will have a variation, right? And the mean value, let's say if I take for resistor, the mean value you expect it to be some nominal value or not, but due to process variation this will change to some plus or minus some percentage of R0. That will be the nominal value, and this is due to the process variation, right? And a typical number for this variation is say 10 to 20%. Okay. On top of it, within a particular chip you will have variation in the component values. So if I call the actual resistance value, this will be the mean plus delta R. R is the mean value. Around the mean you will have variations, and this variation is due to the random mismatch. Okay. So here I plotted the distribution of the total resistance R. I will call it say R total. This contains the mean plus the delta R. So if I plot the distribution of just delta R, how do you think that will look like? This is basically the distribution of the mean R plus delta R. Yeah, if I plot the distribution of just delta R, it will be the same distribution but centered around 0, right? So delta R will have a mean of 0, right? So of course this is now a Gaussian distribution. To completely characterize a Gaussian distribution, what are the things you need to know? Nu and sigma, of course you already know the mean. It's all 0 mean in practice. So we just need to find the sigma. So of course you can define the standard deviation in the delta R. But let us say I have a nominal resistance of say 1 kilo ohm. I find that the delta R is say 100 ohms. Sorry, not delta R, sigma delta R is 100 ohms, right? If I let us say have another resistor which is 100 kilo ohms, what can you say about the standard deviation of delta R here? Do you think, I mean, I have particular resistor. I find that the variation in that resistance value is say 100 ohms. If I increase the resistance value, what can you say about this delta R? I mean, do you think it will be same or it will increase? Increase? I mean, at least if you follow plain logic, it should be 10 times, right? So the point I am getting at is, it is not enough just to say that my sigma of delta R is so much. What is the other thing I need to know? I also need to know the nominal value, right? Without this guy, this alone is not relevant, right? So that is why instead of just saying standard deviation in delta R, we basically normalize this with respect to the nominal value. So this basically is sigma of delta R by R. Because this guy is a constant, taking the standard deviation and dividing it by a constant is same as taking the standard deviation of the quantity divided by the constant. Okay. So this is typically called the relative mismatch, and that is what is usually quantified. Because the absolute mismatch is it's not, I mean, that will not give you the full information because it depends on the nominal value also. So we quantify with relative mismatch. And similarly for the capacitance also, like how we quantified for resistor, even for capacitor we quantify this using relative mismatch.
What was the difference you tell between process mismatch and random mismatch?
Okay, so process mismatch is variation in the mean value from, let us say, one chip to another chip. Okay, now random mismatch accounts for the variations around this mean value in a particular chip. Is that okay?
In the same chip.
In the same chip. Random mismatch, you think of it is an intra-chip variation. Process is from chip to chip. It is variation in the mean value that is captured by the process variation. The spread around this mean within a particular chip that is captured by random mismatch. Is that clear? So, and typically if you find the relative mismatch for passive components, that is around, that can be as low as 0.1%. Okay. So, if you take the, let us say, what that means is, if I look at the variation in the mean value from chip to chip, the mean value can vary from 10 to 20%, but within one chip, if I have 1000 resistors, around that mean value, the spread is very small. Okay. So if you have 100 resistors on a chip, the resistors value within those chips, the variation in them will be not so much, but the mean value can change quite a lot from one chip to another chip. Okay. So this is for passive. So similarly for MOSFET, for quantifying the current factor mismatch, we do relative mismatch like this, delta beta by beta, where beta is mu COX W by L. Okay. But for threshold, we just say it as delta VTH. We don't normalize it to the threshold voltage. Again, one reason is there are some transistors for which the threshold voltage can be close to 0. So it doesn't make sense to normalize with respect to a small threshold. So typically it's just expressed directly like this. So now if I look at all these quantities, let us say sigma delta R by R, sigma delta C by C, sigma delta beta by beta, and sigma delta VTH. All of this turns out that they are inversely proportional to the area. So this is some proportionality constant by square root of area. This will be some proportionality constant by square root of area. This is some A beta times this guy. So this was proved by Marcel Pelgrom. So it's often called as Pelgrom's model or Pelgrom's law. I'll give an example for you to appreciate why this makes sense. But yeah, this is the deal. So all this means is this. Oops. If I want to reduce the relative mismatch in resistors or mismatch in the threshold voltage of transistor, what is the brute force solution? You increase the area. Okay. Now if your process is good, the proportionality constant itself might be so small. But for a given process, if you want to reduce the effect of mismatch, so increasing area is one brute force solution. Yeah. And what is the units of AR? First of all, what is the units of sigma delta R by R? Delta R by R, what is the units of that? Unitless. If I take standard deviation of that, that is also unitless. So what do you think the units of this guy is? Yeah, meters. Yeah. So for everything it is the case except for VTH. For this guy, what is the units? I mean, what is the units of sigma VTH? Volts. So this should be, sorry, volts meter. Cool. So is this clear? So if that is the case, let's take an example and then see how we can calculate effect of mismatch. And in fact, now we can see, right? Let us say if you want to design a resistor, earlier we saw that, oops, yeah, from the value of the resistor you want and the sheet resistance, you know the ratio L by W. Now from the mismatch you can tolerate sigma delta R by R, you can find what should be the area, and based on that you can choose individual Ln width, right? Because this will be given by your process. So for a particular, if you want to tolerate some percentage of mismatch, you go and choose your area accordingly, so that way you can get L and W individually.